Hi guys, we've done it. We've made it through integrals. Yay! All right, so now we have something a little different from the derivatives and integrals we're used to. It's called sequences and series. So we're going to look at sequences here to start. And you might be wondering, what is a sequence? Well, a sequence is just a list of numbers, really. All right, it may follow some pattern. It may not follow a pattern. All right, sometimes we talk about it as a function whose domain is the positive integers. We usually write it like this, a sub n. So we could have like a sub 1 would be the first term, a sub 2 would be the second, a sub 3 would be the third, and so on. And these would probably be numbers of some sort. And each one of these guys is called a term. So there's the first term, the second term, the third term, and so on. We could start at a sub 0 if we wanted to, depending on where we wanted to start with, and a sub 1, a sub 2, and so on. We could use a different letter if we want. We could say b sub 1, b sub 2, b sub 3, and so on. All right, these are all just sequences. All right, if we just make a list of numbers, that is a sequence. These things over here are all examples of sequences. Here is a sequence with a formula. All right, so let's try and list some terms here, and let's just start with a sub 1. So if we started with a sub 1, we'd plug in 1 here. It'd be 3 plus negative 1 to the first, which would give us 2, 3 minus 1, right? And then a sub 2 would be 3 plus negative 1 squared. So this would be 1. 3 plus 1 is 4. And then a sub 3 would be 3 plus negative 1 to the third. So it'd be 3 minus 1 is going to be 2. And then a sub 4 would be 3 plus negative 1 to the fourth. That's going to be 1. 3 plus 1 is 4. Hopefully you can see a pattern. It looks like it's just going to go 2, 4, 2, 4, 2, 4, and so on forever. And that is that sequence. All right, and that's just because we're going from an odd exponent to an even exponent. The even exponents make the one positive. The odd exponents leave it negative. All right, so here's some other examples of sequences. Let's see if we can just real quickly write out an nth terms formula for them. Maybe they might not all be so easy, but for some of them we can. And then like nth term formula would be like this, a formula with n for the sequence. And then we can ask, does it appear to be approaching some sort of limit? So this guy, all right, looks like all of them are fractions except for the first term. So we could say the first term is like that. And it looks like all these guys down here are powers of 2. Like this would be 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. So it looks like we've got 2 to the n on the bottom and just 1 on the top. And we're going from n equals 0, 1, 2, and so on. All right, so now what happens as n increases? What happens as we go to infinity? Well, the bottom's going to be infinite, the top's going to be 1, so it looks like it's going to go to 0. So this sequence is probably going to go to 0. And when it does that, we say it converges. And we'll talk about that more on the next slide. Next one. So let's again make it 1 over 1. So we have 1, 2, 6, 24, 120. Those numbers might be familiar to you. They might not. We're going to go over that more in a couple seconds here. But on top, we clearly have 1. On the bottom, we have a number that's getting much bigger. So it looks like it's going to go to 0. If you're curious, this is exactly n factorial, or n exclamation point, and we'll define what that is in a little bit. The next one here, so we got 1, 3, 6, 10, 15, and so on. These are actually the triangle numbers on the bottom. All right, but on top we've got 10. On the bottom we've got some sort of numbers, but it looks like the bottom numbers are going to keep getting bigger and the top numbers are going to stay 10. So this sequence looks like it's going to eventually go to 0. The next one here, 1, 4, 9, 16, 25. Those are all numbers squared. And squared. 4, 9, 16, 25, 36. Well, those are just numbers squared also, but they start 1 higher. So we'll say n plus 1 squared. All right, and then what does this limit go to? Well, if we went back to just our regular limit rules, this would be n squared. The coefficient here would be n squared. This would be 1n squared over 1n squared. It looks like that would go to 1. All right, and the last one here, it looks like we've got odd numbers on the top. The way we usually write odd numbers is 2n plus 1. On the bottom, let's see, 7 to 10, 10 to 13, to 16, to 19. Looks like we're just going up by 3 each time. All right, so if we're starting at 1, this would be 4 plus 3 times 1. This would be 4 plus 3 times 2. So this would be 4 plus 3n. All right, so 2n plus 1 on top, 3n plus 4 on the bottom, looks like this limit would go to 2/3. All right, so we'll go more in depth in this on the next slide here. All right, so we say the limit L of a sequence, a sub n, is the limit as n goes to infinity of a sub n. All right, let's just take the limit and see what does the sequence go to. Does it go to some certain number or not? If it goes to some certain number, then we say the sequence converges. It has a finite limit. If it does not go to some certain number, we say the sequence diverges. So like it could go to positive infinity, it could go to negative infinity, or it could oscillate. I don't remember if there's two L's in there or one L. Like it could go back and forth between something like high and low and high and low and high and low and high and low and so on. All right, so all the old limit rules that we used before, those are all still applied. Like we can do the sum of limits, the difference of limits. We can pull out a constant. Our exponent rules still work. All that sort of stuff still works for limits. We can compare coefficients, which is what we're going to do here. So here's b sub n. It's n over 1 minus 2n. And we want to find the limit. So we take the limit as n goes to infinity of n over 1 minus 2n. I know some of you thought you were done with limits. No, we're never done with limits. So this is essentially equal to n over negative 2n. As we go to infinity, the n's will cancel. And we just get negative 1/2. There's our limit. All right, so it goes to negative 1/2. So towards the end of this series, it's just going to be negative 1/2, negative 1/2, negative 1/2. Something very close to negative 1/2 over and over and over again. All right, so we would say that this sequence here converges. Because it goes, the limit has a finite limit. There's our finite limit right there. How about this guy? N squared over 2 to the n minus 1. All right, so does this converge or diverge? Does it have a limit? So let me switch colors here so I don't get mixed up. So if we take the limit as n goes to infinity of n squared over 2 to the n minus 1, they're both top and bottom are going to infinity. If we did L'Hopital's rule, we would say this is 2n, and this would still be 2 to the n times the ln of 2. All right, and they're still both going to infinity. So if we did L'Hopital's rule again, we'd have just 2 on top, and we'd have 2 to the n times ln of 2 times another ln of 2, so ln of 2 squared. So the top is now constant. The bottom is still 2 to the n, so it's going to go to 0. So this guy does converge. He converges to 0. All right, so I mentioned the factorial stuff before with the exclamation point. It just means that number times every whole number less than that all the way down to 1. So like 5 factorial is 5 times 4 times 3 times 2 times 1. So that'd be what, 6 times 4 times 5. So 6 times 20 is 120. All right, so n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down to 3 to 2 to 1. All right, and we define 0 factorial to be 1. It just helps us out sometimes. So like here, if we want to find the limit of this guy, limit as n goes to infinity of this sequence, 1 over n factorial. The bottom is clearly going to get very, very big very fast as n goes to infinity. And the top is just going to be 1, so it's going to 0. All right, now we talked about oscillating, like switching back and forth between negative and positive numbers. So what we can do, it's called the absolute value theorem. I don't know if I've ever actually used the name of this before, but if the limit of the absolute value of the sequence goes to 0, then that means the limit of the entire sequence goes to 0. So it doesn't matter if it's going to 0 from the left or 0 from the right. Either way, it's going to 0. So here's our example here. Our b sub n is negative 1 to the n over n minus 1. So this will keep switching back and forth between negative 1 and positive 1 because odd and even exponents. All right, but as we go to infinity, if we just look at the absolute value of that, limit as n goes to infinity of the absolute value of negative 1 to the n over n factorial, well, that's just going to be the limit as n goes to infinity. So we just basically, this is 1 or negative 1, so it's just 1 over n factorial, which is the same as this guy. So it's going to 0. So that means this whole thing also is going to 0. And again, they converge. It converges to 0. And this also converges. All right, and I think the last thing for this section here is we have two other terms that we often apply to sequences. The first is monotonic. is it just going in one direction? All right, mono means one. Tonic, I guess in this case, means direction. So either a sub 1 is bigger than or equal to a sub 2 is bigger than or equal to a sub 3. So in other words, it just keeps decreasing, constant or decreasing. Or a sub 1 is less than or equal to a sub 2, is less than or equal to a sub 3, is less than or equal to a sub 4. In other words, it's always increasing or equal. So if it's always going down or always going up, we say a sequence is monotonic. All right, bounded. So if there's some number, a finite number, not infinity, but like if there's some number, like 10, I don't know, and every term of the sequence is less than or equal to that number, we say it is bounded above, right? It's always less than or equal to some number, right? It never gets up above that number. All right, we say the opposite, that a sequence is bounded below if it's always greater than or equal to some number. All right, so as long as we're always bigger than some fixed number, like it's always bigger than 0, it's bounded below by 0 then. All right, and if it's bounded in both directions, above and below, then we just say that it is a bounded sequence. All right, now here's the neat thing. If a sequence is bounded and monotonic, then it converges. All right, so there's some sort of top to it, there's some sort of bottom to it, and it's either always going up or always going down. We're getting to some sort of horizontal asymptote is what's happening. Like we're getting an HA, all right, and it's going to converge. All right, so here's some examples. Are these monotonic? So this one we looked at before, and it was 2, 4, 2, 4, 2, 4. All right, so it goes up and then down and then up and then down and then up. So is it monotonic? Definitely not. All right, but it is bounded. It definitely is bounded by 2 and 4. It never gets bigger than 4, and it never gets lower than 2. So, you know, it's got the equal to here. If you wanted to, you could say it's bounded by 1 and 5. That would also be true. All right, how about B? So I'll switch colors here for each one. Is this guy monotonic? Well, we could plug in numbers and see what happens. Like if we plug in, say, 0, we get 0. If we plug in 1, we've got 2 over 2, so that's 1. If we plug in, what are we on? 2 would be 4 over 3. If we plug in 3, it'd be 6 over 4. It looks like it's getting slightly bigger here. If we plug in 4, it would be 8 over 5. I think this is still getting bigger, but it's tough to tell. So one thing we could do is we could, you know, pretend it's some sort of function of n and just take its derivative. All right? So we could like say b sub n prime is, or we could, you know, let's say f of x equals 2 to the x over x plus 1, and we can take its derivative and see where is it increasing, where is it decreasing. All right? So if we take this derivative, f prime would be, let's see, on top, let's see, it's a quotient rule, so it's bottom times derivative of the top minus the top times derivative of the bottom all over the bottom squared. So we get 2x plus 2 minus 2x, so the 2x's are going to cancel up there. So on the top we've got 2, on the bottom we've got x plus 1 squared. This is always greater than 0, so that means it's always increasing. I'm going to throw the word always in front of it. All right, the derivative is always positive, it's always increasing. So yes, it's monotonic. All right, we could ask if it's bounded above. I think it is. Like if we look at the limit here, the limit goes to 2. All right, so it looks like these numbers are slowly increasing to 2, so it is bounded as well with a limit of 2. All right, how about this last guy? So this might be tricky to plug in numbers here. What if we just do the derivative trick here? What if we just say, oh, this is maybe, oh, I forgot. I said I would switch colors for each one. Back to red. What if we just said g of x is x squared over 2x minus 1? So then g prime of x would be bottom times derivative of the top minus the top times derivative of the bottom all over the bottom squared. All right, so the bottom's always greater than or equal to 0. All right, how about the top? Not so easy to do that, is it? We could factor out an x. Well, we could actually distribute first, too. So we'd have 2 to the x plus 1 times x minus 2x minus, let's see, x squared 2 to the x times the ln of 2. Gosh, that's not pretty at all, is it? So that does not look pretty. Let's try and just look at some terms and see what happens. All right, if we plug in 0, we're at 0. If we plug in 1, we've got 1 over 2 minus 1 is 1. If we plug in 2, we get 4 over 4 minus 1 is 3. So that's still increasing. What happens if we plug in 3 now? We get 9. We get 8 minus 1 is 7. Doesn't want to write 7. If we plug in 4, we get 16 over 2 to the 4th is 16 minus 1 is 15. And looks like we went down and then went back up. Or it looks like we went up and then back down here. What if we plug in 5? We get 25 over, we plug in 5 here, 32 minus 1 is 31. So we're at 1, then we're bigger than 1, bigger than 1, bigger than 1, less than 1. So we went up and then we went back down. So it's not monotonic. So in this case, it was easier just to look at some terms than it was to try and do the derivative, because that gets kind of ugly. We'd have to use the calculator to see. But it would change signs. It looks like there is a sign change somewhere. It does go from increasing to decreasing. All right, so it's not monotonic. Bounded, I'd say it probably is bounded above, and bounded below, because it never gets below 0. So it definitely is bounded too. All right, so there was a little bit on sequences. The next one we're going to look at is series, when we're adding up all the terms of a sequence.